Hi, let's continue with section 4.6, exponential equations and applications. In this section, our objectives are 1. Solving exponential equations using matching bases. 2. Solving exponential equations without using matching bases. And lastly, we have some applications. Solving exponential equations using matching bases. Because exponential functions are one-to-one, two exponential functions with the same base are equal if and only if their exponents are equal. This process can be used to solve each of the following equations for x. So do you see here how we have that same base? For this one we have a triangle, which is a delta. This one we have a beta. Here we have I believe that's a sigma. All right, so we have the same base, and as long as we have the same base, we can, in a sense, disregard it. So we can go ahead and just ignore the base and only work with our exponents. So that we would have, for example, x equals 3, or 3 equals x, or x equals 3. The idea is that we can go ahead and disregard the bases and work with our exponents only. The answer to each of these equations is x equals 3. Regardless of what the base is, as long as the base is the same on both sides, the exponent of x and 3 must be equal. Following this idea, the step in our process to solve the exponential equations will be to check if it is possible to write an equation as the equality of two exponential expressions with the same base. All right, before we continue, I want to recall a couple of exponential rules. One of them is if I have a number with the exponent raised to another exponent, what happens with those exponents is that they multiply. So that would be the same thing as n times m. They don't add, they multiply. Also, I want to remind you what we do when I have a negative exponent. If I have a number raised to a negative exponent, I can make it positive by writing it as a fraction. So 1 over. And because we have equality, we can go whichever way we want, whichever may be helpful. All right, let's continue with example 1. Solve the following exponential equations. So we see that our bases are 7 and 49. Is there a way to write them so that we have the same base? Well, isn't 49 the same as 7 squared? Yeah, right? So I can change my 49 with something else and keep that base of 7. Considering the bases of 7 and 49, we must recognize that 49 is the power of 7, and we write the equation as 7 times 3x minus 1 equals 7 squared. Now that both sides are the same base, we see that we have a 7 and a 7. Setting the exponents are equal as, so we set our exponents equal to each other. So we have 3x minus 1 equals 2. Now we solve as usual. So we add 1 to both sides, divide by 3, divide by 3. We get x equals 1. Let's continue with example B. Here our bases are 3 and 9. Is there a way where I can write one or both of them so that we have that same base? And we can, right? Because 3 squared is the same as 9. So let's replace that 9 with that 3 squared so that we have the same base of 3. Considering the bases of 3 and 9, you must recognize that 9 is a power of 3. And we must rewrite the equation as, so replace 9 with 3 squared. And remember, this multiplies. So I have to multiply 2 times x minus 1. So we essentially have to take the time to distribute. 2 times x and 2 times 1 gives us 2x plus 2, which we have here. All right, now we have the same base, so we can go ahead and work with our exponents only. Now that both sides are the powers of the same base, setting the exponents equal as, So we have our exponents only, which are 5x minus 4 and 2x plus 2. Now we can go ahead and solve. We can put our x's together, so minus 2x gives us 3x, plus 4, we get 6. So we're left with 3x equals 6, divided by 3, we get x equals 2 as our answer. What about example C? All right, here we have exponents that, bases that are not the same. I have 2 and 3 and 27 and 8. Is there a way to write them with the same base? Well, let's think about 27. 27 is the same as 3 cubed, and 8 is the same as 2 cubed. And isn't 2 and 3 a basis we have on our other side of the equation? Yes, right? So I can go ahead and replace 27 over 8 as 3 cubed over 2 cubed. But that still doesn't fix the issue because I want 2 on top and I want 3 on the bottom. And it doesn't match up. So in order to switch our inequality, we can go ahead, that was a cube for the 3. We can go ahead and raise everything to a negative 1 power. That would cause it to flip. All right, moving forward, let's go ahead and read what we discovered. Discovering the basis of 2 and 3 and 27 and 8, we must recognize that 27 is equal to 3 cubed and 8 is equal to 2 cubed. So we can write it as 3 over 2 cubed. We can now rewrite the equation as, so we're here, but we see that our fractions don't match up. They're not the same base. So let's go ahead and make our exponent a negative to make it flip. All right, we're here. We have a negative exponent and we now have our desired fraction. All right, now that we have the same base, I can go ahead and disregard it and work with the exponents only. So I have x minus 1 equals negative 3. To solve for x, we just move the 1, plus 1, plus 1, and we're left with x equals negative 2. Solving exponential equations. Starting with the first exponential equation in the section, 7 raised to 3x minus 1 equals 49, we were able to use rules of exponents to write every equation as an equality of two exponential expressions with the same base. We will now discuss exponential equations where it is not simple to write both sides of powers in the same base. When we solved 7 with the exponent of 3x minus 1 equals 49, the solution we found to be is x equals 1. Now consider 7 raised to the 3x minus 1 equals 61. All things identical except for the slight increase of 49 to 61. An educated guess for the solution is that the number is a little larger than 1. So how do we deal with such situation? So in other words, this is where we don't have same base. What do we do here? Well, we rely on our logarithm rules. So example 2. Considering the base of 7 and 61, we recognize that the two bases cannot be easily written as a power of a common base. The key to this type of exponential equation is the rule of logarithms. So one of our rules, I think this one's called the power rule. It was the third one from our last section. And this says that if I have an exponent, I can go ahead and bring it forward if I have a log, right? So they're being multiplied. All right. But now our question doesn't have logs, does it? It says we have 7 raised to 3x minus 1 equals 61. Let's take the natural logarithm of both sides. And this is a trick. This is the super important part that we're applying. We're taking the natural logarithm of both sides. So same thing as dividing on both sides, adding to both sides, multiplying to both sides. We can also take the log of both sides, or ln. All right, if we do so, we just write ln on both sides. And by doing so, I can go ahead and now take my exponent and bring it forward. And that makes it easier because I no longer have an exponent an x in the exponent's place. So I have 3x minus 1 times ln of 7 equals ln of 61. Essentially, we have used the power rule of logarithms to bring our variable down to where we can more easily work with it. All right, now what's our goal? Let's go ahead and solve for x. So let's divide both sides by ln of 7. Even though it looks ugly, no, it's just a number. It's an ugly decimal. So we have 3x minus 1. We add 1 to both sides. Lastly, we divide everything by 3. All right, so this is our answer. Now this is done using a calculator. Take the moment to maybe pause the video and make sure you can punch this into your calculator. If I may give a suggestion, first find what ln of 61 divided by ln of 7 is. Press enter. Add your number plus 1. Press enter. And lastly, divide by that 3. And hopefully that gives you the right number. Now, it all depends on what type of calculator you're using. I know some calculators you punch things in different orders. So take a moment to practice this. General process for solving exponential equations. 1. You want to isolate the exponential expression. If the equation can be written as the same base, then you can set the exponents equal each other and solve. Otherwise, you have to take the logarithm of both sides, use the power rule to bring down your exponent, and solve for the variable. So let's take a look at example 3. Solve for the exponential equation. All right, so all we do, we can't write it as the same base. So let's go ahead and take the ln of both sides. Actually, we can't. Why do you think this isn't the case? On our previous problem, do you see how we had just one term equal to another term? We had 7 and 61. They were each one term. Here, we don't have just one term, do we? We have two terms on one side of our equation. So we see that we have to do a bit more work. We want one term equal to another term so that we can apply the ln. One side is so that I can take the log of both sides of the ln of both sides. All right. Let's look at this more closely. What can we do so that we can take the ln of both sides? We need to isolate the exponential expression 4 raised to 2x minus 1 on one side. We can do so by simply adding 5 to both sides. Plus 5 plus 5. Now we have 4 raised to the 2x minus 1 equals 26. Now I can go ahead and take the log or ln of both sides. Continuing, we recognize that the base of 4 and 26 cannot be written as the power of a common base. So let's take the natural log of both sides. There we have it. That's our trick. We do so we can take our exponent, which contains our variable, and bring it down. All right, don't let all this writing fool you. If you're ever unsure, take a moment and think, hey, what are we trying to do? We're trying to get x by itself. All right, let's divide by our number, ln of 4, ln of 4. You use your calculator to find out what that is. We're left with 2x minus 1. We add 1 to both sides. Lastly, we want x by itself, so we divide by 2. All right, so this is our answer. Remember, to get from one point to the next, we use our calculator. Take the moment to practice punching it in your calculator so you can get the correct answer every time. In each example, we took the natural logarithm ln of both sides. We can use any logarithm, but because all scientific calculators have a button for both the natural and common logarithm, we usually stick with either ln or log. So that would be like a log base 10. The next two examples will show the one case where it is more advantageous to choose to use either ln or log. If solving an exponential equation using logarithms and there is a base of 10 using the common logarithm, log is a better decision because log of 10 equals 1 and ln of 10 is ugly decimal. So this would be our better choice. Similarly, if for solving an exponential equation using logarithms and there's a base of e, using the natural logarithm ln is better choice. We see that ln of e equals 1, where the log of e is an ugly decimal, not what we want. Right? And the reason why this is so, we go to section 4.5. That was one of those beginning properties. Example 5. Solve the exponential equation. All right. So I look at 10 and I look at 91, and there's no way I can write the same number with the same base, right? So I need to take the ln or log of both sides. But which is a better choice? Do I take ln or do I go ahead and take log? Log would be the better choice. Why? We see this 10 and log is naturally base 10. So they would undo each other and we're just left with the exponent. We have isolated the exponential expression and the bases 10 and 91 cannot be easily written as a power of a common base. Let's take the logarithm of both sides, choosing log because we have a base of 10. So that's why we're choosing log versus ln. If given an option between the two, we reserve ln when we have e's. But we can always use them interchangeably. Once we punch into our calculator, we'll get the same answer. All right, so let's take a look at our problem. We took the ln of both sides, and we do this because we want to take our exponent and bring it down. And we can do so by our laws of logs. All right, so now we have 3x plus 1 times log of 10 and log of 91. Log of 10, that's just 1. And so we're left with 3x plus 1. Oh, I think they're missing a plus 1. Actually, that's an identity. It doesn't really equal 1. We can just, it kind of undoes each other. So we're left with 3x plus 1 equals log of 91. So we can go ahead and solve for x. That's our goal, to get x by itself. So we go ahead and subtract 1, subtract 1. We have 3x equals log of 91 minus 1. Divide by 3, divide by 3. So we have a log of 91 divided by 3. Again, we use our calculator for this. And our answer is 0.31968. Example 6. Solve the exponential equation 6,000 equals 200 times e with the exponent of 0.5x. All right, so let's take a look at this problem. All right, I see the e. So if I have to choose one of them, I would think ln. But we have a problem. When we apply the ln on both sides, my e is not directly next to the ln. What we want is the ln of e because I know that wouldn't do each other. That would make it go away. So what can we do to get rid of that 200 so that I can have ln and e directly next to each other, just as we see here? All right, we need to isolate the exponential expression. So dividing by 200 gives the equation as 30 equals e raised to the 0.05x. The bases of 30 and e cannot be easily written as a power of a common base. Let's take the logarithm of both sides. Choosing ln because we have a base of e. All right, so we go ahead and take the ln of both sides. By our exponent rule, we can bring this forward, and we're left with 0.05x times ln of e. Ln of e, they undo each other, so that's gone. So we're left with 0.5x equals ln of 3. Remember, our goal is just to get x by itself. So let's divide by 0.05. All right. Lastly, we use our calculator to find our final answer. 68.0239. All right, another example. Our final exponential equation example will have multiple copies of our variable. That makes it kind of difficult. So let's take a moment to do a problem. What if we had 3x plus 1 equals 6x minus 4? How would you do such a problem? Wouldn't you group your x's together and your numbers together on one side of the equation sign, right? So that you would get minus 3x minus 3x, and then you would move your numbers that don't have a variable to the other side. So plus 4, right? So that we have 5 equals 3x and continue solving. Well, same idea. Group your x's and group your numbers on the other side. That would be a helpful trick. Example 7. Solve the exponential equation 3 raised to 2x minus 5 equals 4x plus 1. We recognize that the bases of 3 and 4 cannot easily be written as a power of a common base. Let's take the natural logarithm of both sides. All right, so I take the ln of both sides. That way I can bring my exponent forward. So we have 2x minus 5, ln of 3, equals x plus 1 times ln of 4. At this point, our approach will vary from before. Our immediate goal is to be able to combine both copies of our variable. For this reason, we will have to distribute to give our equation as. So what's saying is that we have to distribute the ln. So we have 2x times ln, and then negative 5 times ln of 3. We have to distribute our ln of 4. So we have x times ln of 4 plus ln of 4. Now we isolate all terms with our variable on one side of the equation, meaning let's get our x's together. What numbers have x's? I have x ln of 4 and 2x ln of 3. I want them on the same side. So let's take the time to subtract x ln of 4. Now what numbers don't have an exponent? Minus 5 ln of 3 and ln of 4. So let's take the time to move them. So plus 5 ln of 3 plus 5 ln of 3. So what are we left with? We have 2x ln of 3 minus x ln of 4 equals 5 ln of 3 plus ln of 4. We do this because we have multiple copies of our same variable, our x. But we want to have x only once. So what can we do? We can factor out our variable. So we can factor out that common factor of x. So what are we left with? Once our x is factored out, we're left with 2 times ln of 3 minus ln of 4. All right, last step, we want to get x by itself. So we go ahead and we divide by 2 ln of 3 minus ln of 4 to both sides. The last two steps have resulted in an equation with a single copy of the variable, which can now be isolated by division. And we have our solution. All right, for this problem, take the time to type it into 2 spots. I would probably take the time and get a decimal for my numerator, and then take the time and find my decimal for my denominator, and then divide at the end to get this answer. But again, practice using it in your calculator. You can also punch it in one shot. Just make sure to use a lot of parentheses so that it knows what you're working with. Applications. The last component of this section will introduce a few examples of many applications that involve exponential equations. Example 7. How long would it take to double an investment if an account earning 5% compounded daily? All right, so we have to recall our formula for compounded interest. Now we have an answer, right? We know we wanted double, so twice as much. We are looking to solve for time t, and we see that t is in the exponent's place, right? And the two specific words are 0.5 and daily, and so we get our equation. So this is our percent. This is daily, 365. Now we're left to figure out t. P and A can be cleverly filled in. The other piece of information is given by a problem of the word double. But how do you know what the number to enter for A and for P? We can enter any number for P as long as A is double. So it doesn't matter as long as A is double. So the easiest numbers to use are 1 and 2. So let's go ahead and enter a 1 for P and 2 for A. All right, so let's go ahead and work this out. Now, 1 times anything gives us itself, so we can go ahead and drop that 1. All right, now our problem is that our exponent contains our variable. What can I do to bring our variable down? Noting the two bases cannot easily be written as powers of a common base, we can take a common logarithm of both sides. So let's go ahead and take the log of both sides. So I have log of 2 equals log of, well, everything else. We can now use our power rule to bring our exponent down. So I have 65t times log of 1 plus 0.5 divided by 365. All right, our goal is to just get t by itself. So everything else, even though it looks really complex, everything else is just a number. So I can go ahead and divide 365 and log 1 of 1 plus 0.05 divided by 365, such as we see here. All right, again, this is calculator work. Our answer should be 13.86. If I were you, I would take a moment, pause the video, and practice punching this in. And once I'm good, I would move forward. All right, moving on, example 8. How long would it take for 500 to grow to 750, an account earning 6% compounded continuously? Continuously is a hint to let us know that we're working with a different type of formula, and that's A equals PE to the RT, which we have here. We are looking to solve for T, and from our specifics, we get an R of 0.06. We have an ending amount and a starting amount, so that we have this formula here. All right, our problem is that our exponent has our variable. So let's use our power rule to rewrite this. To do so, I need to make sure E is by itself. So let's go ahead and divide by 500. Let's go ahead and divide by 500. That's because we want ln of E. We want those two together. All right, so to isolate the exponential expression, we divide both sides by 500, giving 1.5 equals E raised to the 0.06t. All right, let's go ahead and take the ln of both sides. By doing so, we can bring our exponent forward. So we have 0.6t times ln of E. Now, we specifically chose ln because ln of E, that's gone. So we're left with 0.06t. Okay, so we have ln of 0.5 equals 0.6t. We want t by itself, so we divide by 0.06. All right, we use our calculator to get that t is about 6.76. All right, I think I don't want to do the rest. Yes. So I'll take a look at your homework and make sure that it doesn't include problems from here on out. I want to stick with the formulas that we really already know. So that's compound interest and continuously compounded interest. So that's it for this section. I will not cover the rest. It won't be on your homework. It won't be on a quiz. It will not be on exam either. But from everything from here on up is fair game. All right, if you have any questions, you can always email me or post in our discussion board. Thanks.